In this video here, we're going to take a look at conservation of mechanical energy and also the work energy principle. Now we can use the principle of conservation of mechanical energy and also the work energy principle to solve problems involving a moving particle. So when no external forces other than gravity here do work on a particle during its motion, the sum of the particle's kinetic energy and potential energy remains constant. And this is known then as the principle of conservation of mechanical energy. And this is true whether the particle moves vertically or along a path inclined to the horizontal. Now, the total energy possessed by a particle can only change during the particle's motion if some external force is doing work on the particle. So, any non-gravitational resistance to motion acting on the particle will reduce the total energy of the particle. And the reason for that then is because the particle will have to do work to overcome the resistance. So the change in the total energy of a particle is equal to the work done on the particle. And this is known as the work energy principle. So with all that in mind then, let's just work through a practice question on these two concepts. So let's just have a go then at this one practice question here for conservation of mechanical energy and the work energy principle. So what I've got here then is this question. So we have a smooth plane that is inclined at 30 degrees to the horizontal. We have a particle of mass 0.8 kilograms that slides down a line of greatest slope of the plane. We're told that the particle starts from rest at point A and passes point B with speed of 10 meters per second. And all we want to do here then is find the distance AB. So as we can see here straight away, right, we don't have a diagram. So as always, right, let's just start by drawing our own diagram. And again, it doesn't need to be perfect, right, just so we can visualize this problem. So what I've got here then is the kind of flat ground or the horizontal surface, something like that. We have the inclined plane here. Let's just say something like this. And my angle then of inclination here is 30 degrees, right? We've got a smooth plane that is inclined at 30 degrees to the horizontal. And just a quick note here, the fact that the plane is smooth, right, is good. It just tells us that there is no friction to account for with this problem. So what I've also got here then is the particle A. So the particle starts from rest at point A, and it just slides down this plane here. Okay, so let's just say then that this here is the particle A. So that there is A. We've got the weight here acting vertically downwards, like so. So we've got a particle here of mass 0.8 kilograms. So my weight here is 0.8 g newtons there, like so. And then particle A slides down the plane here, and it reaches some point here, B, right? So let's just say that this is this point here. So that's B. Again, this is my particle, okay? And what I want to find here then is this distance in between. Okay, let's just call that here x meters, right? So if I also account for the speeds here, well, particle A starts at rest, so speed here is 0 meters per second. And then at point B here, it has a speed of 10 meters per second, right? And where are we told that? Yeah, so 10 meters per second here. Like so. Am I missing anything else from my diagram? If you want to include the normal reaction here, A, that's absolutely fine. But the normal reaction here, if I also draw that on, if I also call that the normal reaction R here, this does no work, right? Because it's always perpendicular to the motion. So you don't really need to account for that or worry about it as such, but it's completely up to you if you want to include it with your diagram here. Okay? So, because in this question here, the only force acting on the particle that is doing work is gravity, what I need to do here then is apply the principle of conservation of mechanical energy, right? So, what I'm going to start with here then is the decrease in potential energy. So the decrease here in potential energy, P dot E, this here then is equal to mgh. So mgh here, which in this case is equal to 0.8 times 9.8. Then we times this by h here. So h is the vertical distance moved. So just apply some basic trigonometry here. And what we get then is x sine 30 here. Like so. Now what I also want to account for here then is the increase in kinetic energy, right? We have the increase here in kinetic energy, K dot E. Okay, so for the increase in kinetic energy here, that is given as a half mv squared minus a half mu squared. Okay, so we just put that all together here. I get a half times m, which is 0.8, times that by v squared. So v here is 10, our final speed, right? We times that by 10 squared. And at this point here, right, we're just going to subtract a 0 because I've got a half times 0.8 times 0 squared, which all of that then is just 0. So minus 0 here, like so. And as we mentioned before, right, the only force acting on the particle that is doing work is gravity. So we now apply the principle of conservation of mechanical energy. And what that tells us here then is the decrease. So the decrease here in potential energy is equal to the increase in kinetic energy. Okay, so all I now need to do here is equate this, and then just solve for x here, right? Because x here is my vertical distance. Sorry, not vertical distance, but the distance here between A and B. So equating these two things here then, what do we get? So I get 0.8 times 9.8 times x sine 30, like so. This here then is equal to the increase in kinetic energy. That's a half times 0.8 times 10 squared. So a half times 0.8 times 10 squared. And then, like we said here, right, we just want to solve for x here, x being the distance between A and B. So in that case then, x here is equal to, so it's going to be half times 0.8 times 10 squared times 0.8 times 10 squared. And what I do here is I divide by 0.8 times 9.8 times by sine of 30 degrees here. So 0.8 times 9.8 times sine of 30 degrees here. Okay. And at this point here then, what you now need to do is just put all of this into your calculator. And if you do this correctly here then, what you should find is we get 10.2 meters there. Okay. And this here then is to 3SF. Okay. And there we have it then. So this here is the distance AB. So let's make a note here. The distance AB is 10.2 meters there. Okay. Now, obviously, you could have took SUVAT here and the constant acceleration formulae as an approach to finding the distance AB. Obviously, given that we're looking at conservation of mechanical energy and also the work energy principle, I think it makes more sense to take that as an approach here. Okay. But like I said, SUVAT is also absolutely fine here. But there we have it then. So that gives us our solution here. So that's the solution to the one practice question for this video here. And that brings us to the end then of this video here on conservation of mechanical energy and also the work energy principle.